What's good, guys? Welcome back to the channel. So in today's video we're going to be running through the continuity of protective bonding conductors test. Also going to be talking about the theory around the test and bonding and all that sort of stuff too. Before we do, if you haven't already, please like, subscribe and hit that bell button. Let's run the intro. So today, like I said, we're covering the continuity of protective bonding conductors test. It's very similar to the R2 test method for continuity of CPC, but with slightly different application. Unfortunately, the theory is very heavy on this one, much more heavier than the practical. However, the boring stuff is very important when it comes to bonding. If you do know this stuff or you're not interested, you can skip straight to the test procedure via the timestamps in the description. So in these videos, I like to actually talk about the regulations which justify and require us to do what we're doing in the video, this test process. And in today's situation, it's regulation 411.3.1.2. That's the regulation number, and it's titled Protective Equipotential Bonding. The regulation states, in each consumer's installation within a building, extraneous conductive parts liable to introduce a dangerous potential difference shall be connected to the main earthing terminal by protective bonding conductors complying with Chapter 54. Examples of extraneous conductive parts may include metallic water pipes, metallic gas insulation pipes, other metallic insulation pipework and ducting, central heating and air conditioning systems, exposed metallic structural parts of the building. There's also a note that states where non-metallic pipes, for example plastic, enter a building and are connected to the metallic pipes within the building, metallic pipes within the building do not normally require protective bonding as they are unlikely to be extraneous conductive parts. Now, the regulations there set out a requirement for equipotential bonding for extraneous conductive parts, but regulation 643.2.1 requires that a continuity check be carried out on all protective conductors. This includes earthing conductors, the protective conductors of all circuits, all main protective bonding conductors, and where applicable, all supplementary bonding conductors. So the first regulation I mentioned states the requirement to install equipotential bonding where it's needed, in line with the relevant chapters and other British standards. And then this second regulation says that we need to carry out a continuity check to verify that it's there and ensure it's going to function as intended. That is why we have the continuity of main protective bonding conductors test. And that's the test that we're going to be running through in this video. Now, before we get into that test, I just want to talk about the science and theory behind the test and bonding itself. So firstly, the test, you're going to be using a low resistance ohmmeter or a multifunction tester configured to this setting. You're essentially taking a long lead from the MET or the origin of the bond to the other end of it to verify continuity, also see if it's within a prescribed value. But to get into the science and theory of bonding, first we need to understand what bonding is, and to understand what bonding is, we might need to understand what earthing is. Earthing conductors provide a path to earth for fault currents, which protects people and the light, but also gives the protective devices the ability to trip and operate as intended. Bonding conductors ensure that extraneous conductive parts are at the same potential as the electrical installation. That's whether, under normal conditions or fault conditions, it just ensures that they're at the same potential. And it also provides a low impedance path to earth so that, under fault conditions, again, circuit breakers and switchgear and stuff can operate as intended. Both earthing and bonding conductors, one way or another, end up connected to the MET and the earth of the installation, but there's quite a different purpose between the two, and it's just getting your head around that. They're both connected to earth, but an earthing conductor or CPC is very different to a main protective equipotential bonding conductor or a supplementary bonding conductor. But anyone that doesn't know what an extraneous conductive part is, BS 7671 definition is a conductive part liable to introduce a potential, generally earth potential, and not forming part of the electrical installation. Now, you should pay close attention to the fact that it states not forming part of the electrical installation. So it's something that isn't associated or part of the electrical installation that's coming in, introducing a different potential than the potential of the electrical installation. So that's quite important. The idea is you have an electrical installation with obviously loads of exposed conductive parts, whether that's metal consumer units, trunking, whatever. And under fault conditions, an earth fault particularly, those parts of the insulation could raise in voltage. Now you may have a water or gas main that's coming into the building, and this is going to be sat at 0 volts. This potential is actually being introduced from outside of the installation because, you know, the gas or water main is running through the ground, which is basically its own earth electrode. So yeah, that potential is going to be different to, of course, the potential now under fault conditions inside the building. So if you were to touch some of the pipe work and an exposed conductive part of the installation at the same time, there's going to be potential difference there, which is voltage, and that voltage is going to allow current to flow to earth, killing you in the process. Heavy stuff, right? But by bonding these extraneous conductive parts, you can bring them to the same potential as the electrical installation under normal or fault conditions, and the lack of difference in potential there will mean that no current will flow if you were to, you know, touch the two parts. And of course, the low impedance path would allow the offending circuit to trip off as well, thus solving a multitude of issues that can arise from extraneous conductive parts. Now, potential is also something that's often misunderstood, quite hard to contextualize within our jobs as electricians, and to be honest, I've been doing it 10 years and only recently have I fully, have I got a good, what I think is a good grip on what potential is. Now, a good friend of mine, Corey Mack, explained it incredibly well on his YouTube channel, so all credit of this explanation goes to him, but I thought I would use this explanation because it may help you guys understand what potential is. Now, Corey said, imagine if you had two water mains that come out of the ground and then just got connected together. Random, but imagine that. Now, if you fed one of those water mains with 5 bar worth of water pressure and the other with 15, the water's going to come through the pipes, it's going to maybe meet in the middle, but the feed with 15 bars worth of pressure is going to overpower the other one, and the water's going to flow one way. Now, imagine if you put 10 bars worth of pressure up one pipe and 10 bars worth of pressure up the other, the water's going to come up the pipes, meet in the middle, and it's going to butt heads. It's not going to move though, because you've got the same pressure here and the same pressure here. It's going to hit and it's going to have nowhere to go. Now, if you apply that example to potential, and imagine that the bar of pressure is potential and the direction of the water is current flow, you can see that if you have the same pressure, the same potential, water, which is current, is going to meet in the middle, not be able to go anywhere. As if there's a difference in pressure, a difference in potential, the water is going to flow one way, and thus that's where, you know, problems can occur, people can get hurt. So yeah, it's a bit of a random explanation, and I hate giving plumbers any credit whatsoever, but it's helped me get my head around it, and hopefully it helps you guys understand it a little bit too. So we should have a grip on what main equipotential bonding is, why we do it, and of course the theory behind potential. But just quickly, we'll get into the test in a minute, but just quickly, I want to talk about supplementary bonding too, because I think that's quite important. Supplementary bonding is used to connect simultaneously accessible exposed conductive parts with extraneous conductive parts to prevent a hazardous potential difference occurring between them. It's usually only required in special locations, or more commonly in special installations, petrol stations, medical, all that sort of stuff, but they haven't been required as much in recent editions of the regulations due to the prevalence of RCDs and the fact that we use RCDs on pretty much everything nowadays. It's also important to determine whether something is in fact an exposed or extraneous conductive part. If it's an unnecessary bond, you may be allowing faults to be exported to parts of the installation and basically allowing current to flow in areas of the installation where it simply wouldn't be present if you didn't bond it in the first place. So it's important to not only get this right, but also to be aware of previous regulations. The topic of bonding, and specifically supplementary bonding has changed backwards and forwards so much over different editions of the regulations that there's much confusion on this topic. There's a lot of unnecessary bonds out there, and you just need to be considering this sort of stuff when you're inspecting and testing older installations. Now, you can usually determine whether a metallic part is an exposed or extraneous conductive part just by sticking to the definitions set out in BS 7671 to the letter and just applying some common sense. There are, however, some really grey areas and some situations that create great arguments for and against something being an exposed conductive part, which essentially leads to confusion amongst practicing electricians. Now, the IET actually posted some guidance on this, and the guidance suggested if the ohmic value between the suspected extraneous part and earth is greater than 22 kilo ohms, then the part in question is considered as unable to introduce a shock risk and, as such, won't require bonding. To measure this sort of reading, you're actually going to need an insulation resistance tester, and a reading of 22 kilo ohms will actually look more like 0.02 mega ohms. So in this situation, you would test between what you're thinking is the exposed conductive part and the closest earth path, so something that you definitely know is connected to true earth, and do an insulation resistance test between those. Anything over 0.03 mega ohms you would consider not an extraneous conductive part, and therefore it wouldn't need bonding. Now again, apply the definitions and a bit of common sense before you just go around testing everything. A lot of stuff, you know, is insulated from earth and stuff like that, so yeah, just think about it before you do it, because you may be creating more problems than solving them. And, you know, also refer to guidance note 8 or online for more information, because the topic of earthing and bonding is extremely vast. Like I said, I've been doing this 10 years, and only the last couple have I felt like I've got a real grip on it to the point where I could, you know, speak to you guys about it and explain it confidently. And even so, you know, this is probably a bit rough around the edges compared to someone who is extremely knowledgeable on the subject. Refer to GNA and online. There's loads of information out there. There's loads of other great CPD and content on it too. That's the theory, or what I'm calling the theory, out the way. And now let's move on to a few important points before we get into the test procedure. Now, this is another dead test. So on a new installation, you're actually going to carry this testing procedure out before energization, or you should be. So you'll be sweet there. However, on existing or live installations, of course, it is already energized, and you need to verify the continuity of them to carry out an EICR, right? So you need to isolate the installation. You need to isolate it completely, because part of the testing process is going to involve you potentially removing some of the bonds, and as we've just gone through in the theory, without the bonds in place, you've got that potential difference there, and of course you'll actually be touching both parts potentially at the same time. So if anyone's likely to get hurt in that situation, it's going to be the electrician conducting that test if it was live. So yeah, dead test, super important to isolate safely. I've got a full video on safe isolation which I'll link to up here, but yeah, just make sure you isolate the supply. This is a dead test. Now, you've isolated and you think you're good to go, right? You think you're out the woods. Well, you're actually not, because there's one final thing, and that is diverted neutral currents. This has actually been happening for years. However, there's massive talk in industry about it at the minute, and there's actually new guidance on it in Appendix D of GM3 that takes you through a sort of a way to look for them, a testing process. And there's just a lot of talk about it because it's actually quite dangerous. So yeah, I think awareness is trying to be raised. Now, diverted neutral currents are basically where the neutral current of the installation is taking an alternative path because it has to, or it has the ability to. So for instance, if you lose the protective earth neutral conductor to a house, then that neutral current can have nowhere to flow, but there's actually a parallel path through the main equipotential bond onto the water or the gas, which then runs through the ground. So it can take that path through the bond, down the pipe, and actually end up back at this, you know, the supply transformer or earth basically. And that's the path it's going to take, just because that's how electricity works. Now, with diverted neutral currents, they can be imported or exported. So exporting would be you've lost your neutral conductor, you've lost your pen, and therefore your neutral current's got nowhere to go. So like I said, it's going through the main equipotential bond and getting out of the building that way. That's exporting. However, you can actually import them, which is where it gets really dangerous. You imagine next door's lost their neutral conductor, their pen conductor. Their neutral current is flowing through their bond, through their pipe, which then runs next to your pipe. So then it goes onto that, comes up your main equipotential bond into your system, and then is using your pen to get back to the supply transformer. Now, when you isolate your installation, the neutral current of next door is going to have nowhere to flow. It's obviously going to be sitting on, you know, all of the exposed and extraneous conductive parts of the MET and stuff like that. Obviously, that can be extremely dangerous. The current there and the potential difference, you're going to get hurt. So yeah, it's super important to test for these. Obviously, more awareness of it will come now that it's quite a big deal. But yeah, it's just super important, and check out Guidance Notes 3 Appendix D for a full safe process for testing for diverted neutral currents. But yeah, I just thought it's super important to mention that. I'll also have a video coming out on the full test process in the future, so keep your eyes peeled for that. So let's stretch it out, because that was long. A lot of theory, a lot to talk about, but I think it's important. But now we can get to the testing process, the moment you've all been waiting for. So how do you actually test a bonding conductor? Firstly, you'll need a low resistance ohmmeter or a multifunction tester configured to this setting. You'll also probably need a wander lead, which is effectively an extension lead for your probes. Because of the distance between the origin of the installation and the bonds, you know, the leads of your tester probably aren't going to reach. So yeah, you can use a wander lead. Whatever you're using, it's important to have the leads of your tester or the wander lead nulled. So this is a feature of the tester which basically considers the resistance of the lead and removes that from the equation for a clean and accurate result. You can also just make a note of the resistance of the leads and remove that at the end if you prefer to do it that way. You want to start by disconnecting the bonds you want to test from the MET or from the earth bar of the installation. You don't have to do this, you can just clamp onto the earth bar. However, I find it's the best way to initially just negate any parallel paths. The conductor disconnected, you'll want to attach your wander lead to it via a crocodile clip, and then start making your way to the other end of the bond. Once at the bonding clamp, you'll want to connect the other lead to the bonding clamp termination and press test. You should be looking for a result below 0.05 ohms. Now, once complete, you actually want to put the probe on the extraneous conductive part itself and test again, and hopefully get a similar result to the one you just got. The first test tests for continuity and resistance of the conductor itself between, you know, the termination and obviously the other end. But the second test actually proves that you've got a sound connection between the termination, whether that's a bonding clamp or a bolt or whatever. You've got a sound connection between the termination point and the extraneous conductive part. It's all well and good having a nice low resistance piece of cable from the origin to the termination, but if it hasn't got a sound connection to the extraneous conductive part, then it's no good. So this second test just verifies that, and yeah, you're looking for around the same result immediately after the connection point. If both values are below 0.05, then the test is considered satisfactory and it's complete. So that's the test done. Pretty easy, right? Like I said, it's super heavy on the theory and the information and the science behind why we do it. However, when it comes to actually testing them, it's super easy. Before we wrap this one up though, there's a few things I want to talk about to make this as conclusive and informative on the subject of bonding as possible. In the real world, the bonding connection isn't always visible or accessible, more often than not actually. Now, you should try to gain access and locate these bonds. However, where not practicable, Guidance Notes 3 offers some alternative guidance. In this situation, it's acceptable to test between the MET or the disconnected bonding conductor and the extraneous conductive part itself. Now, normally you'd be looking for the required or the GN3 required value of 0.05. However, not all testers go to this low of a resolution, and therefore a value of 0.1 would be deemed acceptable and would satisfy the requirements of this test. It's important, however, to note on the certificate that this isn't a true R2 and that you've actually just tested between the MET or the disconnected bonding conductor and the extraneous conductive part. It's also important to note that you haven't actually inspected the condition and the integrity of the bonding connection, the bonding clamp or whatever it is. So yeah, you are potentially leaving yourself open there. You know, this is for situations when you literally cannot get into, you know, where it's located, or it would require to do damaging works in, you know, a client that doesn't want, you know, is happy to sign that and say, look, I don't want the damage to be done, or in a listed building or something like that. So yeah, it's for use in those unique circumstances. To be honest with you, you generally can find the bond one way or another. But yeah, I just thought I'd mention that because it's interesting to see that alternative guidance in GN3. It's not uncommon to come across conductive parts that have been painted, whether the painter's got a bit carried away or they're trying to blend it in with something, or it's come coated or sheathed in some sort of decorative material. It's not uncommon to find them in this situation. So it's important here to make sure that you're making a sound connection with the raw material of the metallic part. Now certainly don't pierce a copper pipe to get to the raw copper, but yeah, scratch some of the paint off, make sure you're making a sound connection there. Some steel work's been painted and painted and painted again, you know. It's important to yeah, make sure that you're making a good connection to that. It also goes for installing the bonding clamps. If you are fitting a new clamp or something like that and the pipe is painted or the steel work is painted, make sure you get down to that raw mineral there and make sure you've got a good connection with it, because ultimately it's going to provide a better result and a sounder electrical connection. Now in domestic settings, bonding conductors are either 6 or 10 mil. Now to meet the value set out in GM3 of 0.05 ohms, you're going to get about 15 meters of 6 mil and about 25 meters of 10 mil. So that covers most domestic light commercial situations. However, in the commercial industrial world, bonds can be hundreds of meters long. They can be, you know, across vast areas. So just don't be afraid to walk into a switch room and see a 35, 70, 95, 120 mil bond, you know, big, thick earthing conductors. It's just going a further distance. It's been designed accordingly to either meet that value or obviously in accordance with the supply conductors. But yeah, just don't be freaked out when you see those bigger bonding conductors, because it's just on a vaster scale. They don't really tell you that in college, and I found when I stepped out into the big world of commercial industrial, some of these bonds, you felt like you were, you know, disconnecting the earth for London, when really it's just going a long distance and there's a massive supply. So yeah, just don't get intimidated by them. This procedure and this video also gives the impression that bonding conductors need to be at or below 0.05 ohms in total resistance. However, this is actually considered a rule of thumb because the value of 0.05 actually comes from the guidance notes and not from BS 7671. The regs itself purely bases the sizing of bonding conductors on the contents of table 54.8. Basically correlates the size of the bonding conductor, the earthing conductor, with the supply neutral conductor. This point is to keep the regs beavers happy. Most designers I know work to a tolerance of 0.05, and I recommend that you do too. There are also different types of bonding clamps. So there's an EC14, an EC15 and an EC16. So EC14 is for use in dry environments. This is under normal conditions, not under, you know, weird ones. Yeah, red one or an EC14 is used for dry conditions. An EC15 or a blue one is for dry and damp conditions. An EC16 or a green one is for use in dry, damp or corrosive conditions. So not a big deal, but just important when, you know, choosing a bonding clamp, bonding connector, that you select one based on the external influences present and the, you know, the conditions. If it's outside, if it's by the sea, you just want to be making sure you select the right type so that it can last long and not deteriorate, because of course you don't want to install a main equipotential bond and then a year later it's no good, or it's deteriorated to a point where it won't provide you know, a true bond. So just something I wanted to mention there, and shout out to JB Electrical on Instagram for making me aware of this, because I wasn't. I'll put all of his links below. Go check him out. He does loads of loads of educational content. Finally, parallel paths. These can be quite the problem when testing bonds. Two separate bonds that go to two extraneous conductive parts may actually have a parallel path between them through, connected pipe work and stuff like that. Think about a boiler. The boiler has a gas pipe going into it and there's a water pipe going into it. Bond both of them individually. They could be connected together. Firstly, two separate bonding conductors to two separate exposed conductive parts or extraneous conductive parts will test out fine if left connected, even if there's a break in one of them. It's effectively going to perform a loop, so whatever bonding clamp you test at, you're going to get continuity there, thus providing a false reading, because if that parallel path was removed by a change in pipe work, a change in something out of your control, out of the installation, then you're going to have a broken bond there, which obviously gives that rise to potential. So while it's good to use the test method set out earlier in the video on complex installations with multiple bonds and a vast array of extraneous or exposed conductive parts that are all interconnected, it may be more worthwhile to isolate the individual bonding conductors and test them independently before carrying on with the rest of the test, obviously confirm a sound connection to the metallic part and that sort of stuff. This is also a common fault under exam conditions, so any apprentices or learners, just watch out for that one. They might try catch you out there where the bonding tests out fine if you don't disconnect it, as if you independently disconnect the bonding cables and test them alone independently, you might find that one of them's actually broken and that is the fault. But without disconnecting them and following the process to the book, you never actually find that fault. So yeah, just something to consider there. So there you have it, guys. That is the theory and the full test procedure for the continuity of protective bonding conductors. Now, it's important to remember, isolate the supply, test between the termination of the bond and the extraneous conductive part itself too, to make sure you've got that sound connection. And finally, consider parallel paths, because they really can be a nuisance when testing bonding. As always, I hope you found this video helpful, insightful, or maybe you've just brushed up on the process again. As always, if you haven't already, please like, subscribe and hit that bell button. Supports the channel, but if you're liking videos like this in the workshop, me out on site, or whatever, you'll just stay up to date with all the content I've got coming out. Thanks for watching. I'll catch you guys on the next one.